Bharat, request you to unmute the microphone. Mr. Bharat.
Good morning, madam. Good morning. Good morning. Hello.
Good morning. Good morning.
Good morning to all of you, and it is my pleasure to introduce Professor Manjit Kaur, Professor of Physics in Punjab University, Chandigarh, and her PhD degree in high energy physics, and she has also done MCA in computer science. She is the member of the CMS experiment at the CERN LHC in Geneva, Switzerland, which has made the historic discovery of the Higgs Boson in 2001 and paved way for the theoreticians to claim 2013 Nobel Prize in Physics. CMS experiment has been cited in the Nobel citation, and she has, to her credit, number of publications more than 1,400, and citations, it is 48,099. You had a big applause for the citation. And H index, I hope you know about H index, it is 88. And she has guided 14 students, PhD degree, and 2 students are under her guidance right now. 4 students from other universities working on research projects with Professor Manjit Kaur. And funding agencies are DST New Delhi, UGC Delhi, CSIR Delhi, India, TWAS Trieste, Italy. And again, you have to give her a big Max Planck Institute, Munich, Germany. EMFCSC, Eric, Italy. Like that, there are many things, and I am just quoting only few things. She has teaching experience of 38 years and research experience 48 years and administrative experience, member of Punjab University Senate 2004 to 2008, member Punjab University Syndicate 2007 to 2008, chairperson Department of Physics, Punjab University from 2013 to 2014. And positions held: Professor of Physics, Associate Professor, Assistant Professor, and now I will go to the future projects. HLLFC, New Physics Research at High Luminosity LFC, Jet Physics and Electroweak Processes, Linear Collider, Physics of Hadronic Jets with Linear Collider using E plus and E minus annihilation at 500 GeV, setting up the SIPM test laboratory in the physics department, Punjab University. Like this, there are many things. And lastly, I will just make a mention about she has organized and attended a number of international and national conferences and books edited, monthly bulletin of IAPT. What you have got here, Indian Association of Physics Teachers, she has edited, and she is right now the editor. Proceedings of 13th DAE Symposium, Department of Atomic Energy Symposium on High Energy Physics in the year 1998, and research publications, as I already mentioned, that it is more than 1,400. And with this, I welcome.
She is also the
IAPT. Let me make a mention that she is actually the Vice President of North Zone. In IAPT also, she is working a lot, and therefore now I request her to give her presentation. Madam, thank you. Please welcome to this session. Thank you, Madam, for accepting our invitation to be the online platform. Thank you.
Good morning to everyone. Am I audible? Yeah. Okay. Good morning to everyone. And thank you very much, Professor Nagaraju, for such an elaborate introduction. And anyway, I'm just a scientist and working with different prospects here now. Am I still audible?
Yes.
Yeah. Okay. So I would now go over to my talk without wasting much time. And this is the title. And can you see my slides?
No.
Not yet.
Please,
Okay. I have to share, actually. I have to share the screen. Now?
Yes, madam. Yes.
Okay. So the title of my talk today is Probing the Universe with Particle Colliders. What are the challenges and opportunities? And before I go over, I would just like to show you this first slide, which says that for thousands of years, all human intellect had thought that only two possibilities can exist for a scientific statement. Either it's true or it is false. There is no third possibility. When you accept this statement, it doesn't coax your mind for any further query. However, if you just change the last exclamation sign to a question mark, you say, with this statement, is there no third possibility? Then this triggers an alarm in your mind. And the whole scientific discoveries have been revolving around this second statement. You do not simply accept, but you go ahead and you try to find out. Today, what I'm going to talk about is the discovery of the Higgs boson. But what this time I thought is that I am not going to give you any mathematical equations. And I will just go through what is the most fundamental level of thinking. Before we go over to that, this is a slide which shows the Nobel Prize, which was given in 2020. And this was for the discovery that the black hole formation is a robust prediction of the general theory of relativity, and for the discovery of a supermassive compact object at the center of our galaxy. The general theory of relativity has played a very important role in the life of all particle physicists. In 2019, the Nobel Prize was awarded for the contribution to our understanding of the evolution of the universe and Earth's place in the cosmos, and for the theoretical discoveries in the physical cosmology, for the discovery of an exoplanet orbiting a solar-type star. Why I am showing you this? This is because from 1901 to 2021, 115 Nobel Prizes have been awarded so far, and these have been given to 218 individuals. There was only one individual, John Bardeen, who received the Nobel Prize twice. Out of the 115 Nobel Prizes awarded so far, about 40 Nobel Prizes have been awarded only for one topic, and that is understanding of the origin and the fabric of science, fabric of universe. So one can understand that if 35% of the Nobel Prizes are being awarded to this topic, then this topic must be really important. And these Nobel Prizes have been awarded only for answering only two intriguing questions. Are we trying to find out the answers to these two intriguing questions? What are these two intriguing questions? What constitutes the whole universe? Second, how and when did the universe come into existence? This is only two questions which have actually bagged almost 40 Nobel Prizes out of 115 Nobel Prizes. So that itself emphasizes the importance of this particular subject. Moving on, a little bit of introduction. 1927, going back in history, we have Georges Lemaitre. He proposed that the universe came into existence explosively from an extremely dense and hot state of the universe, which was named as the Big Bang theory. The subsequent calculations by scientists showed that the Big Bang happened 13.8 billion years ago. And this calculation has contributions coming from astrophysicists, from cosmology, from particle physics, from all these astronomy included. Soon after the Big Bang was born, soon after the Big Bang, the universe was born and it started expanding. And as a result of which the cooling started, the temperature went down, and even today, it continues to expand. The first observational support to the Big Bang theory came from the Hubble's discovery. And this was as soon as the Big Bang theory came in 1927. Soon after that, in 1929, the American astronomer Edwin Hubble discovered that the distances to the faraway galaxies, they were roughly proportional to their redshifts. Now, just to remind you, what is a redshift? When the object moves away from us, the light waves are stretched into lower frequencies, resulting into longer wavelengths. And hence, the astronomers observed that the light coming from distant stars is redder than they would expect. The change of color is called redshift. This is how the evolution is speculated. This is how the evolution is seen. A time which is mentioned as 10 raised to power minus 43 seconds, if you look at the x-axis of this plot, is the time which is known as the Planck time. Time before that is referred to as the Planck's time. And this is also a very small region around this time when the temperature was as high as 10 raised to power 32 Kelvin. And soon after that, the universe starts expanding, the cooling starts, and the very small part starting from 10 to the power minus 43 to 10 to the power minus 40 or 38 is known as the Planck's epoch. Nothing is known about this part. Then the universe expanded, the cooling started, the forces came into picture, the radiation was dominating, and then here comes a period when protons and antiprotons were formed, electrons joined, and the atoms were formed, galaxies were formed, stars were formed. And today, here we stand almost after 15 billion years of the Big Bang. Here, if you look at the Planck era, which I mentioned very close to 10 raised to power minus 3, all the physics theories, they break down. There are very strong quantum fluctuations which are foreseen. The universe's cooling started, and it also gave rise to the building blocks called matter today. 3 minutes after the Big Bang, these protons and neutrons were combined into nuclei, and a process which is called nucleosynthesis, it started here. 3 minutes, nucleosynthesis, where they joined, they formed matter, and today what we look at, particles, protons and neutrons and other particles called as hadrons, they joined together to form nuclei, atoms, and then stars and galaxies. It took almost 380,000 years for the electrons to be trapped around the nuclei to build matter. And by far, still, the most abundant elements in the universe are helium and hydrogen, the lightest ones. 1.6 million years later, the Big Bang, the gravity began to form stars and galaxies from the clouds of the gases. If you try to look at some sort of relationship between the temperature and the energy, then you can find that this is something like this. Very nearly, you can approximate that at what temperature, what will be the corresponding energy. Now, this is an important relation. Why? Because if you want to recreate the conditions of the universe when it started cooling down, you need to know how much energy is required. This is one of the inputs which goes into building and designing the accelerators. Now, this is how one's imagination runs into that what might have happened when the Big Bang happened. And what is this? Now, this is what is known as the matter was created in the form of plasma. So beginning of the universe started with the formation of plasma. And what was the plasma? This plasma basically consisted of hot, intense quark gluons matter, which is called the quark gluon plasma today, and which was formed. And what is interesting and established today by the theories is that equal amount of matter and antimatter was created. The matter created at the time of Big Bang, it remained constant in the universe even today. The antimatter has disappeared completely from the universe. And this is one of the very intriguing questions which the scientists are facing. What has happened to the antimatter? Where has it gone? This is an important question. This is how we see the composition of the universe today. Today, the universe has very few fraction, 0.03 fraction of heavy elements. The stars they constitute and the free hydrogen and helium, which are the most abundant ones, they constitute about 5%. And then we have these most fantastic ghost particles called neutrinos, which are around, which are abundant in the universe, but they only constitute 0.3% mass of the universe. Remaining 95% constitutes what is called the dark matter and the dark energy. Let's have a look at what is dark matter and dark energy. I'm not going to give you the equations, but what I will tell you is that you can imagine that dark matter is some kind of hypothesized matter. Why hypothesized? Because this is needed in order to explain our existence. It is needed in order to explain the current situation of the universe. It cannot be seen directly with any sort of telescopes, with any sort of microscopes. It neither emits, nor absorbs, nor reflects light, any other kind of electromagnetic radiation. Then how do we know? The presence of the dark matter in the universe is implied. How is that implied? Because there are certain observations based on the astrophysical phenomena and based on the gravitational phenomena, which cannot be explained if we do not have the presence of this dark matter in the universe. Secondly, there are several very thorough calculations which show that if the dark matter doesn't exist, we wouldn't exist. The galaxies would fly apart, or they wouldn't have been formed, or they will move so fast that the whole universe will disintegrate. So it's the presence of the dark matter which is keeping the whole universe intact, though expanding at a small rate. The dark energy, again, is something which is needed, which is present. And this dark energy is the one which is causing the universe to undergo expansion. The expansion of the universe is accelerating, which means that this dark energy is some kind of intrinsic energy, intrinsic to the empty space, which has a repulsive nature. This is the energy which is actually pushing the galaxies away. It's the space between the galaxies which is expanding, but not the galaxies themselves. Therefore, the presence of the dark energy is also important. Again, the dark energy must be propagating in a very controlled fashion, which is controlled by some mechanism, so that the universe doesn't fragment instantly. Now, this is an interesting picture. Here you have the living and the non-living. The human mind is very inquisitive. If we try to go back into the universe, we imagine, we wonder how the universe came into picture. And here, this imagination, when stretched too far, goes into the scientific discoveries. And here today we find, in a pursuit to find the structure of matter, we find that everything that belongs to this universe, may it be living or non-living, has the same content. This is something hard to believe, but this is what happens. The scientists have been, for centuries together, the scientists have been looking for what are the fundamental constituents of matter. And the first fundamental science started with 1808, starting from Dalton's atomic theory, where we thought that we have basic building blocks of matter which can be visualized in some form. It evolved that some kind of atoms later on established that they constitute the whole matter in the universe, and these atoms are the basic building blocks. They cannot be broken down. For almost a century, the discoveries followed this pattern, and the atomic physics evolved a lot. There were a lot of theories which came into atomic physics. Then came the next step. Again, the inquisitiveness to see what is inside an atom led us to the discoveries which said that atom has a central core, and the central core is a nucleus. And then started another stream of science, which was called the nuclear physics. And the nuclear physics basically was studying two entities. It was studying the nucleus and it was studying what is surrounding the nucleus, which is the electronic clouds, to form the atom. Now, stretching the human imagination to the next level to query what is inside a proton or a neutron. And then you start with another branch of science, which is called the particle physics, subatomic physics or the particle physics. Subatomic physics also refers to the nuclear physics, but here the particle physics refers to the constituents of the protons and neutrons, constituents of the subatomic particles. This is a branch which started much later. It actually diverted, the nuclear physics diverted into the particle physics with the ultimate pursuit, the ultimate hunt for the fundamental constituents of matter. Today, what we know from all our scientific knowledge, we have solids, the matter around us, the matter in the universe, can be seen, can be visualized to be formed of molecules, atoms, nuclei, nucleons, and then these nucleons have also been looked into by different mechanisms, and we know today that inside a nucleon we have more fundamental particles called quarks and gluons. When we compare the scale, we go from 10 raised to power 9 meters, the size of the molecule, up to 10 raised to power minus 18 meters, the size of a quark. When you go from 1 centimeter up to roughly few micrometer, 3-4 micrometers, you can engage a simple light microscope, a sophisticated light microscope, and you can visually see these things with a microscope. But when you talk of the molecules of the atoms and others, you need to engage more sophisticated microscopes. And then what comes in picture is an electron microscope. However, with an electron microscope, you can go up to only a fraction of a nanometer, but you cannot see dimensions which are smaller than the nanometers. For example, you can't see the nucleus, you can't see the atom, you can't see the nucleons, you can't see quarks, and so on. Therefore, the scientists who were, as particle physicists, trying to discover the quark, trying to isolate the quarks, the constituents of the nucleons, they needed to develop much more sophisticated techniques to go into the details of finding how does a quark look like. Today we know, all of us know, that there are 4 fundamental forces in nature. And these forces in nature are electromagnetic forces, weak forces, strong forces, and gravity. All of us are very familiar with electromagnetic. We know the electric currents. We are very familiar with the strong forces. We are familiar with gravity. We are staying on the earth because of gravity. However, not many of us have a good feel about the weak forces. The weak forces are the forces the most important for the existence of the human being. I'll come to that a bit later. The first 3 kinds of forces, electromagnetic, weak, strong forces, they are very well understood in terms of what is known as the theory of, most accepted theory of the particle physics today is called the Standard Model. The Standard Model came into existence, it started in 1965, and then it is fully developed now. And the Standard Model tells us that the matter interacts through these 3 forces. These are the forces. The matter interacts with each other. Matter stays intact only by the mediating forces. And these mediating forces are mediated between the entities, between the particles, will follow the electromagnetic forces through the propagation of these fundamental particles, fundamental bosons. These are electromagnetic forces. We all are familiar with photons. Strong forces mediated by gluons, not all of us know. Gravity, which is presumably mediated by the exchange of a particle called graviton, which has not been discovered so far. The weak forces are the forces which actually stand out in the sense that they are mediated by the particles which are called W plus W minus and Z0. Here we have a single particle, single particle, single particle, but here we have 3 particles. And what is more intriguing is that all these intermediate particles have zero masses, but this one has massive particles. These are the intermediate particles which actually mediate a weak force. So how we look upon the universe? We know the weak force being mediated, and we also know the electromagnetic force. These two forces were joined together to form what is known as an electroweak force. The beginning of the Standard Model also started with the electroweak force theory. When you join electroweak force and strong force, one forms what is known as a gut force. It is a grand unified theory which explains this one. And when you join this with gravity, you get what is known as a total theory of everything. But this is called a superforce. Why do we want to look at this? Is because here we are going in a backward direction. This superforce existed when the universe came into existence. And all these forces, they are the manifestations of a single force, single superforce. The temperature of the universe, when it fell down to 10 to the power 32, that was the time when the single superforce would have split into two distinct forces. And these two distinct forces were gravity and gut force. So here, what the scientists are doing, a lot is known about weak force, almost everything about electromagnetic, about this one. We know a lot about the gut forces, but the gut forces have not yet been united with gravity, which means that the Standard Model of particle physics includes three kinds of forces, but it doesn't include gravity. That is one of the shortcomings of the Standard Model. However, till today, Standard Model is the only theory which has been most successfully engaged, which has been most successful in explaining the matter. All the fundamental matter in the universe, all the fundamental structures, they can be described in terms of only two kinds of particles. And these two kinds of particles are fermions and bosons. As all of you know, that fermions are half integral spin particles and bosons are integral spin particles. These are the ones which were actually taken into account the Standard Model, and then the Standard Model explained Big Bang. The Standard Model created its own periodic table, inspired from the chemistry, where we have a periodic table which very nicely documents all the elements existing today. This also created its own periodic table. A total of 61 fundamental particles belonging to the periodic table can all be fitted together to construct the entire fabric of the universe. And today, this is one of the most intricate, most beautiful theory of particle physics. What does it say? In the Standard Model, this is the periodic table of the particle physics of the universe, out of which the whole universe can be created. It's interesting to see that it has only these 6 entities called quarks. And these quarks, up, down, strange, charm, top, and bottom, 6 kind of quarks. Each quark has its antiparticle. And this antiparticle is anti-up, anti-down, and so on and so forth. And each quark or antiquark exists in 3 different flavors. Then we have the electrons and neutrinos and muon, tau, and this set of particles here is known as leptons. The first column here, which includes U, D, E, and neutrino, constitutes what is known as the first generation of matter, first generation of fundamental particles. Particles belonging to the second column are second generation, and so are the ones corresponding to the third generation. We have this 4th column here, which shows gluon, photon, Z boson, and W bosons. These are the gauge bosons. They are called gauge bosons because they follow certain gauge theories. Here, these are the bosons which actually cement together the quarks in order to construct matter. Then there is another one. Now, if you look at this one, this green table here, it shows that the masses of these quarks are very small, 3 to 4 mega electron volt. This strange quark has 95, C quark has this one. So in every here, these masses are so small. And if you look at in high energy physics today is a very interesting thing. There is a supposition which is made, which says H by 2 pi C, H cross C is equal to 1. You put H cross C you put H cross equal to 1, C equal to 1, and then you redefine your units. When you redefine the units, what you get is you can express the masses in terms of energy terms. This is only to simplify the life so that you don't have to mention you don't have to mention they saying that you have so many grams of mass here. Today, all visible matter in the universe is made up of only first generation of these quarks and leptons, U, D, and C. Now comes the Higgs boson. Higgs boson has been one particle missing link in the standard model, which was the extremely hard nut to crack, which was extremely hard to find. And for several decades, people were hunting for Higgs boson starting from 1964 onwards, and it was not found. However, the standard model could be seen. Now, this is a very interesting example of this here. Let's look at this very quickly. If you start with this one, you see this girl, and if you try to see what is the minimum smallest thing that you can see is a hair. If you go to this hair, you see the size of the hair is in terms of certain microns. And if you try to go further down, the strands of hair can be split into a single hair. And the single hair can actually be seen as made up of very small 100 micrometer single hair. You go to inside this single hair, you can see the cells, which are 10 micrometer. Each cell made up of 10 micrometer. Now, each cell is made up of macrofibrils, which are 1 micrometer. And each micrometer has microfibrils, which is roughly of 10 nanometers. Going further down, you get protofibrils, which are only 2.8 nanometers. Then further going inside the protofibril, you get keratin, which is 2 nanometers. And if you go inside a keratin, what you see is it is made up of carbon, oxygen, nitrogen, sulfur, all these atoms. Now you go inside the atom of each one of these, any of these, you can see inside the carbon, you have the electronic cloud, and then you have the electron orbitals. And then inside, you see what you see is a nucleus. And this nucleus is made up of large number of protons and neutrons. Now you break up a nucleus, and inside you see protons and neutrons. Now you break up a proton, and you see inside the quarks. The proton size is 1 Fermi, and the size of a quark is less than 1 Fermi. So now the whole idea of showing you this is the stable matter made up of only up and down quarks. If you reverse, if you start from here and you go back, you can see that you joining together all the quarks and matter, you can come back to this beautiful girl. This is how the whole universe was created. Okay, going further. How do we look into a particle? As I mentioned that the electron microscope is not of any help. So the scientists have now discovered building up what we call today are the super microscopes. The super microscopes do not actually show you visibly something, but it consists of millions of electronic channels to look inside a proton or a neutron and to see what are the constituents of the protons and neutrons. Now, starting with these small quarks whose masses were so small as 3 and 4 MeV, if you join inside a proton 3 quarks, by simple mathematics, you will come across 9 or 10 MeV. However, the mass of the proton is 1 GeV, 938 MeV. How come this mass? How come uniting 3 quarks build such a big particle? How was the matter formed? And why does the matter have mass? It was in 1960 that the Peter Higgs gave a theory. And this theory hypothesized that the whole universe is filled with what is known as a Higgs field. And this Higgs field, whenever any sort of distortion is created in this field, it gets excited and it splits up a sort of particle which is called a boson. Through the empty space, all throughout us exists the Higgs field. And when the field gets excited, a tiny chunk, a component breaks off called the Higgs boson. The Higgs boson was also nicknamed as the God particle. Now here I come to the standard model once again. The missing link Higgs boson. The standard model was accepted. People started making big experiments in order to hunt for Higgs boson from 1970 up to 2012. All experiments failed. And this was a big challenge. And this challenge actually, how could scientists prove this theory? There were sophisticated methods to catch these particles. As I mentioned, the super microscopes. And the interesting thing is, the smaller the entity you want to discover, bigger are the instruments needed. And what are these instruments doing? They will try to actually create a lot of energy so that this energy could be converted into a Higgs boson. These experiments started with the particle colliders. They accelerated particles, they collided particles, and then they tried to see what happens in a collision. These were extremely, extremely expensive experiments, could not be afforded by any single country. There were so many challenges. And what were the challenges? Over the 40 years, so many experiments failed to detect the Higgs boson because there was no information on the mass of the Higgs. There was no information how it couples to the particles. What are its properties? How much energy is required to produce it? What are the technological difficulties that we have to face? And this actually resulted in 1980s as one of the biggest hunt in the scientific history. Very simple theory. Theory of relativity, which was the backbone for all these experiments. This was that we knew that energy can be created from mass and mass can be created from energy. And this simplest, beautiful theory created the Higgs boson. In the year 2000, by year 2000, starting from 1970s, it was clear from all the previous experiments, they could not discover Higgs boson. And they put a limit that if the Higgs boson exists, its mass must be greater than 105 GeV. That is what brought into existence the Large Hadron Collider at CERN. The Large Hadron is a word stands for strongly interacting particles. And hadron basically here was a proton. So this was basically a large proton collider. This is an accelerator which accelerates the proton beams and then it collides. It also accelerates the nuclei and smashes them on other nuclei. LHC was planned and designed to recreate the conditions which prevailed a few moments after the universe was born. This was the place which was designated. This is CERN, Geneva in Switzerland, where the Large Hadron Collider exists. The Large Hadron Collider is basically, it is a tunnel of 26.8 kilometers under the ground on the Jura Mountains between Switzerland and France, and it produces the head-on collisions between protons and also ledons. This is how it looks like in the night. You can see this is an imagination. Underground, you have this tunnel of almost 27 kilometers, which houses the beams carrying protons. Now here, how it is happening. So one thing which is very, very important to know, that if you want to accelerate a proton can be produced from a single hydrogen atom by stripping off the electron, and then you can get a proton. But the proton has a mass 930. Its basic fundamental energy is around 1 GeV. Rest mass energy is 1 GeV. If you want to accelerate it to a very high energy, what do you do? How do you accelerate? We know that we can accelerate particles by putting them in the electromagnetic fields. But how much field is needed, how much energy is needed must be calculated. Also, we know that no particle can be accelerated to a speed which is very close to the speed of light in a single go. It must go through several steps. For example, this is what is happening at Large Hadron Collider. We have a booster which first actually converts this into sorry, I'll go a bit slow. So here is a booster which actually accelerates the particle to 1.4 GeV. Then this particle is made to enter the next one, which is a proton synchrotron, 25 GeV. And then after that, it goes into 25 GeV booster. And after the 25 GeV, it enters the third one, which is called a super proton synchrotron. It will now enter a super proton synchrotron 450 GeV, 6.9 kilometer diameter. Then it is made to enter the Large Hadron Collider, where its energy can be increased to 27 TeV. Now, once this happens, then this is the tunnel through which the pipes which carry the Large Hadron Collider, which carries the proton beams. These proton beams are then made to enter. This is how the protons now look like, where the energy is very close to the energy of the speed of light. They are then made to enter the apparatus, which is called a detector. This is the CMS detector. The two particles, two protons coming from different directions, hitting each other, smashing, and producing a very large number of particles here, where the energy has been converted into mass. The energy is 14 tera-electron volt. Currently, it is operating at 13 tera-electron volt. And this energy is now converted into these particles. Most of these particles are pions and protons and neutrons and several of these electrons. Okay, this is now the collision rate is very high. The collision rate is something like 10 to the power 9 collisions per second. But here we select only one event out of so many, 10 to the power 10. This is the rate. Why? Because most of the collisions are not useful for scientific discovery. So there are sophisticated ways of doing that by using electronic channels. Now, this is again the same graph that I showed you, the expansion of the universe. This is where now currently the Large Hadron Collider sits. It actually tries to imitate the conditions which happened soon after the Big Bang, almost 10 to the power minus 12 seconds, 10 to the power minus 10 seconds, very close to this one. These were the earlier experiments which were doing the archaeology, and they were close to 10 to the power minus 6. However, this LHC, Large Hadron Collider, will have proton-proton, and then it will also have ions. So it will try to imitate, it will try to recreate the universe as it was at this time after the Big Bang, and then study what happens. The search for Higgs boson took very long. And this was how this was happened was the basic and the simplest idea was create a lot of energy, and so much of energy so that this energy is enough to create a Higgs boson with a mass which is more than 105 GeV, because up to 105 GeV, it couldn't be discovered in the earlier experiments. What is a Higgs boson? Anyway, there's another way of, simple way of describing it. It is a particle. It is a boson. Currently, it is a boson with zero spin. It propagates force or interaction amongst other particles. And what are these other particles? These are called fermions. When these fermions interact with the Higgs field, they gain mass. And this is how the matter came into existence. Now, there are gigantic detectors. These detectors are the apparatuses which the different countries jointly made. They took it to the Large Hadron Collider site. They were put, and the collision point was fixed in between so that the particles, so that, as I just showed you, the beams come and they hit, the protons go undergo interactions, and these particles which are produced are recorded in these detectors. There are two complementary detectors. This is the CMS compact muon solenoid detector, which is a huge detector. It weighs 14,500 tons. It has various sub-detectors which record different kinds of particles. And here you can see the size of a human in comparison to the size of this detector. This detector was built in part, different parts were built in different countries. They were shipped to CERN and then assembled there. In India, in our university also, we built a part of what was known as the Hadron Calorimeter, HCAL. Indian government supported this venture, and India is a part of the CMS project. There are, at that time, there were only 4 institutes, and currently we have 10 institutes from India which are participating in the CMS experiment. ATLAS is another complementary experiment which also detected. Both the experiments, the first aim was to detect the Large Hadron, the Higgs boson. Now, understanding the creation of the universe from the perspective of the fundamental science. And one of the main goals of the CMS experiment was to search for Higgs boson, the so-called God particle. And the other experiment, ATLAS, also was designed to find the Higgs boson. The question is, why 2 experiments? And the answer is that if one experiment detects a particle, there must be a confirmation in an independent way. And therefore, these 2 experiments were designed in different ways to detect the particle. And both the experiments almost simultaneously discovered the Higgs boson. This is how the actual experimental picture which we took when the experiment was going on. And this is one of the events which was recorded in the CMS detector, and it shows the presence of the Higgs boson. July 4, 2012, the God particle was discovered. And almost 20 years at the LHC, it took so long. The first prediction for the Higgs boson was made in 1964, theoretically. And so many experiments were done. And it is 50 years after the theoretical prediction, the Higgs boson was actually discovered. Who discovered it? As I just mentioned, the 2 experiments, the teams of scientists, engineers, computer scientists from all over the world, different 172 institutions in ATLAS, 177 institutions in CMS, and this is almost around 3,000 scientists in each of the experiments. They discovered this. The Nobel Prize in 2013 was awarded to the original proposers of the Higgs boson. The theoretical discovery of the Higgs boson came from these 2 gentlemen, Francois Englert and Peter W. Higgs. They are from University of Brussels, Belgium, and Edinburgh, UK. Thankfully, that the Nobel Foundation or the Nobel citation mentions that the Higgs boson has been recently discovered through the discovery of the predicted fundamental particle by ATLAS and CMS experiments at CERN. So this fundamental particle mentioned was the Higgs boson. The name boson, you know, is also linked with the Indian scientists. Why is it so important? Why was it so important? The billions of dollars were spent on this experiment. And why is it so important? The important is that should the Higgs field be only slightly different, we would never have come into existence. Should this field disappear or become unstable, we would cease to exist instantly. Therefore, we are existing because of the presence of this Higgs field. And hence, in order for our survival, we must understand what are the properties of the Higgs field. It costed $4.6 billion in the first go, before the discovery of the Higgs boson. And the cost of the detector runs into millions of dollars every year. The mass of the Higgs boson, which was discovered, is 125.6 gigaelectron volt, which is equivalent to this mass, 10 to the power minus 22 grams. Here, 1 GeV is equivalent to so many grams. What is its size? The size is 10 to the power minus 17 meters. As I mentioned to you, the quarks are of the size of 10 to the power minus 18 meters. What is the relevance of the Higgs for a layman? And the relevance is the answer comes from the sun. The massive wealth of hydrogen and helium, which were the most abundant elements in the universe at the time of creation, it loses weight at the rate of 4.3 million tons per second. The question is, why whole of helium and hydrogen hasn't burned so far? The one answer comes from the Higgs theory, which predicted the Higgs boson. And it explains the slow burning of helium and hydrogen and how the right amount of heat and light is emitted by the sun. Here in this part, I have not written the last part completely. This is a question to all the participants of NSSP, all students. I have just mentioned here that the answer comes from Higgs theory, predicted by Higgs boson, and the slow burning of this one. How come the theory is connected with this? Please go back and try to find an answer here. There are opportunities to carry forward the research. And what is this research? The research is the Higgs field is interacting mysteriously with the dark matter, with the dark energy. And since the dark matter dominates our universe and the dark energy is equally important, therefore, the role of the dark energy, which is driving the expansion of the universe, a lot of research is needed in that. Secondly, the gravity is not a part of the standard model. Recently, there has been experiments, LIGO experiment, which detected the gravitational waves. In connection with this, currently, the field of astrophysics, the field of particle physics is alive. And a lot of research is going on to look into these questions. Unanswered fundamental questions related to the Higgs field and the Higgs boson, which may play a gateway role to many mysteries we are facing every day. So it's for the young students to learn deeply this subject. This subject has a lot of potential. This subject has a lot of related research. This is, however, you must understand, this is a research which relates to the fundamental science. This is not the application. However, the application science comes from the development. In order to study the fundamental science, you must also develop the latest technology, use latest technology, develop techniques. This experiment involved not only the physics was a main one, but it also involved a lot of sophisticated technology, and so much of development of this technology took place. And it's really, really very, very fascinating field. And I wish you all that many of you would get inspired and get into this kind of research. Thank you for your time and patience. I stop here.
Yeah, madam, could you take some questions from the students?
Sure.
Yes, any student, if he or she is come to this place and ask the question. Yes, madam, one boy is asking.
Yes, yes.
So, okay, so
Here?
Camera.
can speak here. But my face no.
Yes.
Come this side.
Mic is
Okay.
here.
No, wait. I will do it. So, ma'am.
I can see him.
So thank you very much, ma'am, for such an inspiring talk. What I wanted to know is that you just said that Higgs field is the basis of all the higher order fields that create the visible universe. So is the Higgs field somehow interacting with the dark energy scalar field? If yes, are we studying these kinds of interactions at the LHC or in its upcoming versions?
Okay. Good question. So LHC is now being upgraded to high energy and high luminosity in order to increase the rate of energies. So the next steps, once the Higgs boson has been discovered, we want to collect a lot of data in order to fine tune the properties of the Higgs boson and hence the Higgs field. The interaction of the Higgs field with the dark matter still is not very well documented. It's not very well calculated. It is not known. But that is the next step. I mentioned in my last slide that the next steps is now currently ongoing is the search for dark matter. And once you dark matter and dark energy, that is definitely one of the goals of the future LHC. The LHC, high energy LHC is coming up, and then the high luminosity LHC will also come. The high energy would be increasing the energy basically to 27 TeV so that more particles with higher masses could be created, or the Higgs boson could be created in abundance so that to study their properties in a fine way. So a lot of research for dark matter is going on.
Yes, any other student? Yes, come here. Madam, another student is coming.
Morning.
The question is very basic, but I wanted to know that how does Higgs field play a role in us existing? How does it play a role in our existence? What does the Higgs field do actually in this space?
Okay. So as I mentioned that finally the basic constituents, we have come down to a level where the basic constituents are the quarks and gluons. The quarks, today's stable matter is made up of only U and D quarks. U and D quarks have very small masses, only 3 or 4 MeV. Now, if the proton contains three quarks and gluons. Now, here we have the gluonic fields in addition to this one. At the time when the Big Bang happened, everything was in a fluid state. We had isolated quarks, we had isolated gluons. They started combining. How did they gain mass? How could you construct, how could you make a proton of 1 GeV coming out of few MeVs? So initially the interaction of any particle passing through the Higgs field makes it massive. If there is no Higgs field, no particle can gain mass. That's the whole idea. And the mass in the universe exists only because the particles interacted with the Higgs field gained mass. Otherwise, everything will be in a state of quarks and gluons, isolated quarks and gluons, no mass at all. So the universe could not be created. That's it.
Okay. Yes, madam, there is one more question.
Hello, ma'am.
Hello.
Yeah.
Hi.
So, ma'am, I want to ask you about grand unified theorem. One thing that one professor from Alabama State University, he was doing imaginary energy. He introduced that term that a charge has two portions. One is for one due to its gravity, what is having for real energy, and due to its electrostatic movement or something due to imaginary energy. Using that, he actually tried to equate gravitational energy as well as the electromagnetic energy and all. So, ma'am, what are the aspects of that? Is that?
So that is basically going into the direction of a super force. Because the standard model does not include your gravity. It includes 3 kinds of forces, but doesn't include gravity. When you imagine, if you have charge only, you imagine only of the electromagnetic force. But the charge being divided in terms of gravity also would mean that the inclusion of the gravity as such. And then why superforce? Because the superforce, it says that all 4 kinds of forces are the manifestation of a single force, and that's a superforce. So that must be in the direction of creating a theory which leads to the theory of everything, TOE, not gut. It's combining gut with gravity.
Yeah, ma'am, they all have used that Sudarshan's idea,
Yeah.
Imaginary.
Yes.
Thank you.
So now I request Professor G. Venkatesh. I think there are no other questions. I request Professor G. Venkatesh to thank Professor Manjit Kaur. Please, sir.
Good morning, madam.
Good morning, sir.
I hope you remember me.
Sure, sure.
Now, I will add a few comments before I thank you.
Yeah,
See,
sure, sir. Welcome.
earlier, researchers used to have in gardens at the time of Newton or in patent office room at the time of Einstein. Now you know that for research in nuclear particle physics, you require millions and billions of dollars. And not one country, 20 countries, more than 20 countries are associated with the CERN.
Yeah.
And then lot of supercomputers, 20 supercomputers in different parts of the world. Now, and individually, you cannot get a Higgs boson. So you have to have a teamwork and a huge budget and collaboration. And that is why, see, this is very important. The discovery of Higgs boson is important. Having visited CERN long back, I just want to tell you one thing. Madam has mentioned the energy of two protons colliding is about 7 tera-electron volt. You may be surprised, what is this tera-electron volt? 1 tera-electron volt energy is nothing but the energy of a flying mosquito.
Mosquito, yes. Yes. Yes, yes.
No, I knew that you have missed this point. That is why it is really wonderful. And I thank Professor Manjit Kaur for her excellent presentation of the topic. Thank you, madam.
Thank you, sir. Thank you for giving me this opportunity to interact with these.
Thank
Maybe
you.
I'm able to motivate some of them to go in this direction.
Definitely, Doctor. Thank you, madam.
Okay.
Yes.
I now request Dr. G. Venkatesh to present a brief biography of D.P. Khandelwal. Okay.
Let me introduce